we can start. So, okay, so good afternoon, everyone. Welcome to this NITheCS webinar on Thursday afternoon, the 1st of April. So, and although it's the 1st of April, this is not a joke. We'll have a very serious talk just now. It is a pleasure to introduce Dr. Paola Obando. Paola did her PhD at the university, at the Federal Fluminense University in Brazil, and is currently a postdoc at the Brazilian Center for Research in Physics in Rio. Yeah, and we met Paola a few months ago because she took part in the summer school that we organized in February, and there we started interacting, and she kindly agreed to give us a talk on her recent research. So Paola, thank you very much for being with us today. I know that it's probably quite early for you in Brazil, but thank you for the effort. Yeah, and. With me on the panel, you see Ilya, who is the standard co-host of this event, and Camille, who is a postdoc in my group, and he also has some strong Brazilian connections. That's why we asked him to join us this afternoon as well. Yeah. So Paola, please, you're welcome to share your screen. And while you do that, I just remind people to please make use of the usual Q&A facility or to raise the hand if they want to ask questions during or after your talk. So Paola, please, you are welcome to start with your presentation.
Well, thank you so much for giving me this opportunity, Francesco. Yeah. Well, good evening, everyone. I would like to say thank you for this opportunity to give this talk. It's to me an honor to stay here. Let me introduce myself. My name is Paola Obando. I'm a postdoc at the Brazilian Center of Research for Physics. In my presentation, I would like to tell you a little about one of the works that I've been working in my postdoctoral stage, entitled Macrotomicro, Quantum Mapping and Emergence of Nonlinearity. This article could be found in archive in this address here. Well, let me begin with a little motivation. Quantum mechanics is at the core of our understanding of the physical laws. Two fundamental concepts of quantum theory are quantum correlation and quantum coherence. Both develop an important role as a physical resources for several quantum computation and quantum information tasks. The current development of quantum technologies depending on the capability of transferring information in a coherent way. But in realistic quantum systems, the observation and control of the physical properties is often impeded by the coupling the system to the environment, noises. In this context, theories that model this kind of phenomenon have been widely studied, mainly for their relevance in potential applications. The open quantum system theory is one of these. So the open quantum system theories allow the description of the wide range application in quantum physics where the isolation of quantum system is not possible, the full description of the system, the full microscopic description is not plausible, or in quantum system where the control of degrees of freedom of the environment is not viable or it is only partially. In this theory, well, only partially. In this theory, the kind of interaction between the system and the environment is crucial at the moment of defining how the open quantum system evolves. So, one question that comes up in this scenario is, what happened when the split between the system and the environment is not obvious? Well, as one of the answers of these questions, we find the formalism that involve coarse-graining models or effective quantum systems. Thus, this theory looks for the answer to this kind of a question, as well other open questions in open quantum system theory. Well, the main idea of the coarse-graining models is to simulate the behavior of complex systems using a simplified representation. By the effective description, it's possible to investigate the types of dynamics that could emerge from a full description of a given system when we don't have access to all degrees of freedom. For instance, due to either miss or divide resolution or experimental limitations. In general, a full description, a full microscopic approach is impractical, and it would give an intractable amount of information. Well, the usual division between the system and environment from the open systems theory, it is substituted in this framework for the division between accessible and non accessible degrees of freedom. As a universal theory of physics, quantum mechanics must assign states to every level of description of the system, and also describe the interconnection among them. Due to this universality, we have two ways to understand the nature. The first way that leads from macroscopic level to microscopic level, and the second way that leads from the microscopic regime to macroscopic regime. Our works use the theory of coarse-graining maps with the aim to describe how quantum mechanics leads with these both ways, including the case where the distinction between the system and environment is clear, or system with initial correlation or strongly correlated. The first direction, leveled at micro to macro, allow us to understand how macroscopic characteristic behavior emerge from microscopic description. Here, the main idea is to keep only the degrees of freedom that we can manipulate. So in this imaging, we have in blue the set of all microscopic states that are mapped through the coarse-graining operation lambda to the unique effective macroscopic state represented by the red cat in the left. Well, the opposite duration, labeled as macro to micro, is usually covered by the theory of quantum statistic physics. Broadly speaking, the path that leads from the macro level, represented by the red cat here, and to the micro level, blue cats on the right. This map is known as average assignment map. So this map A lambda assigns a macroscopic system, a microscopic state given by the average over the ensemble of all microscopic states that comply with the macroscopic observation. So our work was built is the same map. In other words, the construction of the macro to micro map. Let me continue now with the coarse-graining map theory. So in general terms, supported by the quantum channel formalism, a coarse-graining operation is defined by a completely positive and trace per set map, or CBPF map. So the coarse-graining operation lambda connects description with different numbers of degrees of freedom. In other words, if we imagine it that a quantum state defined in the Hilbert space HD with capital D describes the microscopic system with a big number of degrees of freedom or a full description, the coarse-graining map takes the system to the level of description where only few degrees of freedom are considered. Thus, the coarse-graining map connects system description with different numbers of degrees of freedom in such a way that the D capital here is bigger than D. A usual coarse-graining situation can be found in open quantum system scenario. In this case, we have an open system interacting with the environment. The composite system is system plus environment is considered closed, and it's defined in this space here, where H is the subspace related to the system, and each A is the subspace related to the environment. Through partial trace operation here, it is possible to access the open system information. The partial trace operation is a coarse-graining operation due that this operation maps the full description of the composite system to an effective description related with the open system, reducing the description to only the system of interest. Well, the formalism of coarse-graining map can also model isolate quantum system submitted to measurement with imperfect resolution, as we can find in experiments with cold atoms in an optical lattice. Here, a periodical oscillation potential is constructed by contrapropagating laser beams. The atoms are trapped in each potential minimum, like here in the picture. In this type of experiments, the spin state is detected by fluorescent imaging technique, where the atoms are illuminated with a laser in a way that the no-excited atoms spin up state, no light is scattered, while for excited atoms spin down state, light is scattered and by the atom and detected by the high resolution microscope, giving us a result images like it is here. We are interested in model this scenario when, for example, this case here, where the neighboring atoms cannot be resolved. So having in mind this kind of experiments in previous works of my research work group, it was established the theoretical model for this specific coarse-graining channel. In this model, called blurred and saturated detector, are considering only two atoms. The situation is the following. Well, let's suppose that the length of detector available is not good enough to resolve the light coming from each individual atom. In this situation, the states 1, 0 and 0, 1, for example, cannot be distinguished. Also, imagine that the amount of light coming from the single atom is already sufficient to saturate the detector. So, having two excitation or one excitation leads to the same signal. In such condition, an effective description becomes convenient. So we have here the mathematical expression for this coarse-graining map that leads two atoms here to one atom. Well, we can see here that the population terms. First, in the first situation here, we have both atoms are not excited, leading to 0, 0 at the effective state. And then for the exciting term, this situation here, the exciting term in the effective description come from three different situations. When we have excitation only for the atom from the right, we have this state here, or the atom for the left, this situation here, or when we have excitation from the two atoms, we have this situation here. Well, the coherence, the effective coherence terms are relating with signal. Well, remember that only we can measure coherence between signals that I can discriminate. So I have coherence term between no excited subspace 0, 0 and the excited subspace 0, 1, 1, 0, 1, 1, 1. Leading the term 0, 1 at the effective level. And finally, for coherence with within the excited subspace cannot be discriminated by the detection process, so their elements are equal to 0 in the effective level. Well, let me continue now with the opposite relation, a macro to micro way. Well, considering that the macroscopic description on our system of study is based on the set of observable quantities, for example, the values that are obtained in the laboratory through some kind of measurement instrument, this operation is given for this equation here. And this work, we assume that the macroscopic description is a coarse-graining version of a microscopic quantum system. So the set of observable quantities is represented here by the capital O, with NO observed quantities or mean values. Each element of this set is given by the mean values of these coarse-graining observables, OE, and are going to be determined by this operation here. Being psi, the pure macroscopic state at the microscopic level. Well, this microscopic state satisfies this macroscopic state that satisfies the macroscopic constraints is not unique. So we need to define a set omega for all possible microscopic quantum states that satisfies this constraint here. Well, the question addressed in our work is how do we connect our macroscopic description with the set of microscopic states? Our contribution in this way, it was called a average assignment map, A lambda. The assignment map is construing, making an average over the set of microscopic states that correspond to the constraints of the macroscopic state or macroscopic observation, obtaining this equation here, where d mu is the Hart measure over the pure states, P lambda is the probability density of having a microscopic state given the macroscopic constraints imposed by the set O, and giving a coarse-graining map. Well, in the case where psi doesn't belong to the set omega, this density probably is equal to 0. In the particular case where the set is tomographically completely, I mean, O is big enough to allow the full state reconstruction, we obtain lambda between the two states, psi or rho for this example here. Well, therefore, we applied our formulas for the case of lurid and saturated detector, where the coarse-graining lambda BNS was previously defined. The effective description comes from the imperfect detection of the two-atom system. The set of microscopic states subject to the constraint is given by this equation here. If we consider it the rho in a given computational basis, the average assignment map is given for this equation here. Here we can see nonlinear terms here and here and here with respect a rho. Remarkably, these nonlinear terms here are related with the coherence which the detector cannot resolve. At the effective level, remembering that at the effective level of all these terms vanish. I mean, after the coarse-graining map is applied, all these nonlinear terms vanish. After the characterization of both ways that leads in the direction macro to micro and the opposite way, we studied the effective dynamics that can arise from the unitary evolutions when we only have access to the coarse-graining description of the system to construct the microscopic work. Well, to prepare the effective initial state rho 0 at the time t equals 0 means to prepare a microscopic state from the set omega lambda, where omega lambda is given for this structure here. Well, remember that this set have this constraint defined by the coarse-graining map. Well, if psi1, for instance, is the microscopic state selected with a given probability and the first run, at the macroscopic level, this state evolves via the unitary evolution ut, and finally, applying the coarse-graining map, we obtain the final state rho 1t in the first run. All this leads in the ith run to a rho ith, given for this composition here, with its probability. Our aim is to obtain the final effective state or the evolved state. So this procedure has to be performed many times, and an average appears given for this equation here. If we reorder in these terms using the fact that the unitary evolution and the coarse-graining map are linear, we can find this expression here, where the highlight term corresponds to the average assignment map for a given coarse-graining. So the final effective state of the evolved state is given for this formula here. Well, therefore, in a nutshell, considering the initial row at the macro level, the average assignment map connects this state with the initial state at the microscopic level. Then we have the microscopic unitary evolution, and finally the action of the coarse-graining map that leads to return to the macro level, where we've obtained the effective state evolved. The resulting effective dynamics have this structure here, and it's represented by gamma T. So we consider in our work the effective evolution for two coarse-graining channels. First, for the case of open quantum system, considering that the coarse-graining map is given by the partial trace, the average assignment map was calculated and given as a result of this product state here. And the effective evolved state have this equation is given for this equation here, where the effective dynamics is linear on row 0, and also given that the unitary evolution and the partial trace are completely positive operations. Gamma T here is a completely positive operation also. Well, for the second example, we consider the blurred and saturated detector. For this coarse-graining map, the effective evolved states is given for this equation here, where the average state for the blurred and saturated detector is have a nonlinear dependence, as I previously discussed. Is nonlinear dependence on row 0 here. So this may lead a nonlinear effective dynamics. Well, also given the unitary evolution and the coarse-graining map are completely positive, the effective dynamic gamma is also completely positive. Well, as a final point, I like to describe how nonlinear dynamics can be useful in the task of discriminate between two effective states. So suppose the following situation. Alice have a source that prepares with the same change when one of two states, the state row and the state key. Alice sent this state to Bob, who makes a measurement. The maximum probability that Bob identifies which state was produced, to correctly identify which state was sent by Alice, is given for this equation here, also known as Hellstrom bone, where D is the trace distance between the states row and key. Notice that increasing the distance between the two states, we have a bigger probability of distinguishing between them. Also, from the quantum information theory, we have another important result. The distance between two states doesn't increase by the action of the linear CBPF map, given for this expression here. So from this result, we can see that the probability of distinguishing between two states can now increase for further linear processing. Well, our intention at this point is giving a specific sample to see how effective evolution affects the distinguishability between two states. So let's consider it two effective initial states, row 0 and key. And we assume for this example that the unitary evolution in the macroscopic regime is given by the local Hamiltonian here, and the effective dynamic gamma is given for this composition here. It is nonlinear due to the nonlinearity of the blurred and saturated assignment map. Well, we have in the figure the distance between the two effective states, initial effective states, represented by the red dashing line that correspond here in the figure at this line here. Then we can see the distance between two initial microscopic states where we have applied the blurred and saturated detector. The blurred and saturated average assignment map represented by the dashed blue line here. And finally, the continuous red represents the distance between two evolved states, two evolved effective states. So we can see how the nonlinear effective dynamics can increase in some regions the distinguishability between two states. But remarkable, the best effective discrimination here and here is never better than the best microscopic discrimination, even by this blue line. Well, let me conclude my presentation. In this work, we formalizing and generalizing the microscopic ensemble assignment, fixed a set of microscopic constraints. Stochastic nonlinear effective dynamics may emerge from the deterministic linear quantum evolution. We see this present framework as a first step toward more general statistic physics. And this work have impact on foundational aspects like quantum to classic transitions, but also in quantum technologies. Well, this work was developed as a part of my postdoctoral research at the CBPF. It is a Brazilian physics research center located in Rio de Janeiro, Brazil, South America. And this work was developed in collaboration of the research from the CBPF, Raúl Valejos and Fernando de Melo, and Pedro Silva Correa. He just finished his PhD last week, and myself. Well, Thank you so much for your attention.
Yeah, Paola, thank you very much. It was an excellent talk. Thank you very much. It was really very interesting. And I would like now to ask Ilya and Camille maybe to guide us through the question and answer sessions. And I'm sure both of them will have some questions for you.
Okay.
Okay. So Camille have lost his internet connection again.
Okay, sorry.
It looks like, but
sorry,
I think, yes.
Sorry, I didn't notice that. Sorry.
Yeah, and so far I don't see any questions in Q&A, so I will encourage people to type their question in Q&A facility, or because there is not too many of us, you can just raise your arm and we can give you a chance to talk or to ask your question. Okay, so my question would be very simple. It's like, kind of when we're talking about linear, everybody know what does it mean. And when we're talking about non-linear, it could mean kind of everything which is not linear. And what kind of non-linearity do you have access to within your approach? Kind of like, what sort of non-linear dependencies can you?
Yeah, we define the nonlinear in this case. For example, when we calculate the average assignment map, we have structure here, and in the coherence terms here we find this behavior here. For example, 1 over row 0, 0, this element here at the square. So we define the nonlinear dependence in terms of the coarse-graining of the state at the effective level.
But does it need to be kind of like because right now it looks like a homogeneous polynomial, so you have a rho 0, 1 modulus squared but divided by rho 0, 0. Does it need to be like so that it's kind of order 1 in the elements of the density matrix, or it could be something different?
I see this nonlinearity like this kind of nonlinear dependence between these elements related with the macroscopic state. I'm not sure if I understand the question.
Okay. The question is more related to the fact that that if we could use some tricks from the open quantum system approach and we can define some nonlinearities, you can use it as a simulator of some other physical nonlinearities. That's where I'm kind of.
Okay. Yeah. I'm not sure.
And that's why I want to know which classes are available.
We don't work in this part now. We only define this nonlinearity with respect to the macroscopic level, but it's an interesting point. I need to research about. Yeah.
Okay, and there is a question in the chat. In the context of transitions between micro and macro, what do you think it would mean if you had a fractal behavior?
Fractal behavior. It's a very interesting question, and due to the nonlinearity of, for example, this map here, but I really don't know. To be honest, I really don't know what we expect if we have a fractal behavior between these regimes. I'm sorry, but I can't see with the how applied this formalism in this coarse-graining and average assignment map.
Okay.
Ilya, can I ask a question?
Of course.
Yeah, no, thank you. Paola, sorry. Your map, for instance, what we are seeing now, yeah? Is it possible to sort of unravel it for the wave function of your reduced system? What kind of equation comes out for that?
When you
No, what I mean is you derive a map for the density matrix, yeah, with your nonlinearity and everything. Yeah.
Yes.
Is it possible to write a similar formulation just for the wave function of your reduced system?
Just for the wave function of the reduced system, let me think. I'm really not sure, because we construct this average same map. We have this restriction here, and all the mathematical calculation was doing with this, considering this constraint here. Let me think, because when doing the mathematical expression, I think it's possible, Professor.
Okay, okay, that will be very interesting.
Yes, I think it is possible. Yeah.
Okay. Then
I need to check.
when you know how it works, you can give us another talk. Yeah, no, perfect. That would be very interesting to see. I would really like to see that. But okay, that's maybe it's another discussion for another day. Yeah.
Yeah.
Thank you. Ilya, are there any more questions in the, no, not in the chat. Anybody who raised the hand?
No, I don't see anyone.
Okay. Yeah, no, then Paola, then thank you so much. That was really very interesting. And I think we will probably have to go and read the preprint. Thank you for reminding us of the archive number. And maybe we will come back to you and we'll have a chat on to see if there is anything that we could do together in the near future. Yeah. But
Professor, thank you so much for the opportunity to give this talk again. It was
absolute pleasure, and I hope that we will keep interacting very, very soon. And sorry that Camille, who is our Brazilian connection, internet problems, but we recorded the talk, so he will have the opportunity to watch it offline later. Yeah. So Paola, then, yeah, no, thank you very much, and have a good day. And yeah, and all the best for the long Easter weekend. Yeah.
Okay, thank you so much. Thank you, everyone, for attending my seminar.
Nice and safe long Easter weekend to everybody. Yeah, thank you.
Oh, bye-bye.
Bye. Thank you very much.
Thank you. Bye-bye.
Thank you.